The purpose of this video is to teach you about the concept of limiting reactants in chemical reaction, both in a qualitative and quantitative way, and also to be able to prepare you to complete this worksheet on limiting reactants. So let's get to the slides first. So we have already encountered limiting reactants and talked about them sort of in a qualitative way in our class so far this year. If you remember back to the reaction in which we put iodine and zinc into a test tube and then added water, after we added the water, the iodine dissolved in the water to give a sort of brownish yellow color. And we had a chunk of zinc in the bottom of the test tube. And so those were heated for a day or two in a hot bath on a hot plate. And when the reaction was over, the yellow color of the iodine had disappeared, but there was still some, not all of the zinc left, but at least some of the zinc left in the bottom of the test tube. And so this is the reaction that we were doing. We were taking metallic solid zinc, and we were reacting it with iodine in an aqueous solution. And the product of that was zinc iodide, which is also soluble for the most part in water. And so that was an aqueous solution. Zinc is a silver solid. Iodine, the aqueous solution of iodine, was sort of a yellowish brown. But the product, zinc iodide, was colorless. And so we knew the reaction was over when the iodine color disappeared. But when we were done, there was still zinc left over. And therefore, we identified iodine as the limiting reactant. It was the reactant that ran out first and limited the amount of zinc iodide product that we could make. And then the zinc we decided was the excess reactant because some of it was left over when the reaction was done. Okay, well, we've talked just also qualitatively about the concept of limiting reactants. I think I've brought up in all my classes the idea of just burning wood. So you have a pile of wood, you light it on fire, and when it's through, you have a little pile of ash, although ash is not really the product of the reaction. Ash is really just that tiny portion of the wood that won't burn. What you're doing, and this is in no sense a balanced equation, because I haven't given a formula for wood, but wood reacts with oxygen. Wood, which is basically made up of carbon, hydrogen, and oxygen, reacts with oxygen to produce carbon dioxide and water. And we agreed that the reaction ends when we run out of wood, because there's basically a limitless supply of oxygen in the atmosphere. So oxygen is always going to be the excess reactant, and wood is going to be the limiting reactant, and the reaction is going to end when the wood runs out. So let's just sort of let's define limiting reactants in a chemical reaction. The limiting reactant is the reactant that runs out first, and the reaction ends when it's used up. So in the two examples we were talking about, iodine was the limiting reactant when reacted with zinc. Wood was the limiting reactant when reacted with oxygen. It's called the limiting reactant because it limits how much product can be made. The reaction will only run until the limiting reactant runs out, and then we can't make any more product. So the question we want to be able to answer when this is all through is, if we're given quantities of all reactants in a particular reaction, how are we going to tell which one is the limiting reactant? And how are we going to be able to tell how much product we can make? And just to ask a simple question, is the limiting reactant simply always going to be the reactant that we have the smallest amount of? Well, let's take a look at this. And instead of looking at reactions first, let's just look at some simple processes involving objects. So let's take the simple example of, I want to run a lab experiment in my class where kids are going to burn magnesium in a crucible to make magnesium oxide. I need to know how many lab stations I can make, so I know how many groups to groupinate the class into. And so here's my equation for a lab station. I need a ring stand, and I need a Bunsen burner, and those two together are going to make a lab station. So here's my balanced equation. Ring stand plus Bunsen burner yields lab station. Okay, well, I go and look in my cabinet, and I discover that I have 10 ring stands, and I have 6 Bunsen burners. So this may seem like an obvious answer, but let's kind of go through it in a systematic way. Um, I could make as many as 10 lab stations from my 10 ring stands. I can make as many as 6 lab stations from my 6 Bunsen burners. Therefore, in terms of, if we think about this as being like a reaction, the Bunsen burners are going to run out first, and therefore my expected yield is going to be 6 lab stations. Okay, well that one was kind of easy. Oh, and by the way, this kind of supports the idea, well, that whatever I have the smallest amount of is the limiting reactant. But one of the reasons that works out that way in this instance is because there are no coefficients in this reaction other than 1. So let's try something else. You guys all know that, or maybe you don't know, but I always like making a ham and cheese sandwich in the lunchroom for lunch. And then I also have the class at the beginning of the year write a recipe for ham and cheese sandwiches. So here's my balanced equation for a ham and cheese sandwich. 2 slices of bread plus 1 slice of cheese plus 1 slice of ham gives me 1 ham and cheese sandwich. So the difference here between the one I was just showing on the previous slide is that now I've got a coefficient for the bread that is not 1. So let's see how that affects things. So I go in my kitchen and I look to see how much bread and cheese and ham I have, and I find out that I've got 10 slices of bread, I've got 6 slices of cheese, and I've got 7 slices of ham. And so from my 10 slices of bread, I could make as many as 5 sandwiches because it's 10 and then 1 sandwich for every 2 pieces of bread, so that's 5. I could make as many as 6 sandwiches from my cheese, from my 6 slices of cheese, and I could make as many as 7 sandwiches from my 7 slices of ham. The bread is going to be therefore the thing that runs out first, and I can make, and my yield, my expected yield, is going to be 5 sandwiches. And so the object of this example is to say it's not always the reactant. The limiting reactant is not always the reactant I have the smallest amount of. In this instance, I had the smallest amount of cheese, but it was the bread that was limiting. So it's not the reactant I have the smallest amount of, it's the reactant that produces the smallest amount of product. So that's the thing to be keeping in mind. Well, so far we have been talking about objects, and objects are rather simple because when we're talking about objects, we're only looking at numbers of items, and that basically corresponds to moles in a chemical reaction. But we've been learning stoichiometry, and so we know now not only how to convert moles to moles, but we also know how to convert mass of one substance into mass of another. Furthermore, we're not typically given chemical compounds as a quantity, like here's 2 moles of bread and 5 moles of cheese. When we're talking about a chemical reaction, we're given our reactants by mass. And so we need to be able to account for the masses that we're given of our reactants. And it also involves using their molar masses, and we've looked at this in Roadmap 2. And so this is a more involved calculation, but we have learned and have started to get confident with the idea of using Roadmap 2 to do mass of substance A to mass of substance B calculations. But it's still going to come down to whatever reactant runs out first and produces the smallest amount of product. That is going to be consistent with what we've already learned. So let's take a look at 2 examples. So let's go back to the example that we talked about in the beginning, which is the lab experiment we did with adding the zinc and the iodine. So let's say I'm giving you this balanced equation, and I'm just going to create some quantities. The quantities could be anything. In this case, I'm simply going to say I've got 1 gram of each. I've got 1 gram of zinc, I've got 1 gram of iodine, and my question is, what's the limiting reactant? Which one's going to run out first? And how much can I make? So we are going to do it in this way. Well, first of all, let me just say, we're asking ourselves, what's the limiting reactant and how much of the product can I make? Let's talk about a systematic approach, which is similar to what we talked about on the slides with the objects, but involves stoichiometry calculation. I've got my reaction. I know how much of each I have. What I'm going to do is I'm going to use Roadmap 2, and I'm going to use Roadmap 2 to go from grams of substance A to grams of substance B. Well, what is substance A and substance B in this instance? Well, I actually need to do two roadmap 2 calculations, and this is how I'm going to do it. First of all, I'm going to do a roadmap 2 grams of A to grams of A to grams of B calculation in which zinc is substance A and zinc iodide is substance B. So in my first calculation, zinc is going to be substance A, zinc iodide is going to be substance B, and I'm going to see how much zinc iodide I can make. Then I'm going to do a second roadmap 2 calculation of grams of A to grams of B in which iodine is substance A and zinc iodide again is substance B. And now I'm going to take my 1 gram of iodine and see how much zinc iodide I can make from that. Once I've completed both of these two calculations, I'm going to look to see which calculation gives me the smallest amount of product. And that starting material is going to be the limiting reactant, and the amount of product I get from that starting material is going to be my expected yield. So here we go. We're going to do the first option first, in which zinc is substance A and zinc iodide is substance B. I'm going to do a roadmap 2 calculation. I've got 1 gram of zinc on roadmap 2. If you've got it in front of you, you can look at what the steps are. And the first step is I'm going to divide by the molar mass of substance A, which is zinc, and its molar mass is 65.4 grams. Then I'm going to multiply by the mole ratio of B over A, which in this case is 1 to 1. And then I'm going to multiply by the molar mass of substance B, which is zinc iodide, 319.2 grams. In any stoichiometry calculation like this, you're going to need to work out molar masses of all the components. You may remember these molar masses actually from the lab experiment we did. The 319.2 was the molar mass of zinc iodide. If I use, so based on my calculation using 1 mole of zinc, I could make 4.88 grams of zinc iodide from 1 gram of zinc. Now let's do the second calculation. In which now substance A is iodine and substance B is zinc iodide. So now I'm starting with 1 gram of iodine. This is a new substance A, so I'm going to divide by the molar mass of my new substance A, which is 253.8 grams. That's the mass of 2 moles of iodine atoms, because iodine is a diatomic substance. Then I'm going to multiply again by my mole ratio, which in this case is once more 1 to 1. And then multiply by the molar mass of the product. And that gives me 1.26 grams of zinc iodide. Well, it's the iodine that gives me the smallest amount of product, and therefore it must be the limiting reactant, and my theoretical yield in this case, or my expected yield, is going to be 1.26 grams of zinc iodide. It's always useful to ask yourself, does this make sense? I would say that it does make sense if I'm putting in 1 gram of each of these and one of them is going to be used up completely. The mass of my product is going to be more than 1 gram, but it's going to be less than 2 grams. I'm going to use one of them up completely, but I'm not going to use both of them up completely. So my theoretical or my expected yield should be somewhere between 1 and 2 grams. It's not possible, based on the law of conservation of mass, to make almost 5 grams of product from 2 grams of reactants. Here, my expected yield winds up coming between 1 gram and 2 grams. Let's look at one more example, because this is another instance in which all of my coefficients were 1. Let's look at an equation in which I've got coefficients that are not 1, and therefore now my mole ratio actually impacts this in a significant way. This would be the combination of aluminum with oxygen to give aluminum oxide. We learned back in Unit 2 how to use the periodic table to work out the formula for aluminum oxide. Aluminum is in group 3, so it forms a +3 ion. Oxygen is in group 6A, so it forms a 2- ion. When I do my crisscross, I get Al2O3. Then I balance the equation and I get these coefficients. And let's just come up with some new masses for these. Let's say I've got 2.35 grams of aluminum and 2.25 grams of oxygen. And I'll describe why I made them a little bit different from each other at the end. Well, we're going to do the same thing. We're going to do the roadmap 2 calculation where aluminum is substance A and aluminum oxide, my product, is substance B. I'm going to start with my 2.35 grams of aluminum, and again, using roadmap 2, I'm going to divide by the molar mass of substance A. For aluminum, that's 27 grams per mole. Then I'm going to multiply by the mole ratio, which is now not 1 to 1, but 2 to 4. And then I'm going to multiply by the molar mass of aluminum oxide, which turns out to be 102 grams per mole. And I get 4.44 grams of aluminum oxide. Well, that's looking good based on what I said so far, because it is more than either of the two reactants, and it is also less than the total of the two. The total of the two actually add up to 4.6. But let's try oxygen next. And so this is now the calculation where oxygen is substance A and aluminum oxide is substance B. I'm going to take my 2.25 grams of oxygen, divide by the molar mass of O2, which is 32. 2 oxygen atoms in a molecule of oxygen is 32. Multiply now by my new mole ratio, which is not 2 over 4, but 2 over 3. Then multiply again by the molar mass of aluminum oxide, which is 102 grams per mole. And I get 4.78 grams of aluminum oxide, which actually turns out to be more than the sum of the two things I put in, which is 4.6. So again, this not only is the larger of the two numbers, but it violates the law of conservation of mass. Therefore, my limiting reactant, the thing that's going to run out first, is going to be my aluminum. And the maximum amount, the expected yield of aluminum oxide I can make is 4.44 grams. I used different masses of aluminum and oxygen just to try and make the point again that it's not always the thing that I have the smallest amount of that's the limiting reactant. In this case, I had the smallest amount of oxygen, but as it turned out, the aluminum, which I had slightly more of, turned out to be the limiting reactant. Well, this should now prepare you to do the worksheet. The first side of the worksheet is just based on the sort of combination of objects concept that I was looking at in the original, in the first part of the slide. And then on the back, I've got 3 combination reactions for you to look at. The first one you'll be familiar with because we just did a calculation on the zinc iodide reaction in the slides. But I'm just giving you different starting masses in this case to look at. Then another combination reaction to make methanol from carbon monoxide and hydrogen, and finally a combination reaction involving phosphorus and oxygen. Thanks so much for watching.